Log on, tune in, find out. Another good idea from Cambridge.
Holger did make a comment that what we seem to be doing these days in designs is simply applying the equivalence theorem, and I'm afraid I'm rather guilty of that. But anyway, this is a talk simply on logistic regression with two variables, and the first thing I'd like to say is it is very much joint work with Gaëtan Cabrera from the MRC in Durban and Principal Mshlovu from the University of South Africa, Pretoria. Now, if you know the geography of South Africa, you'd wonder how someone in Cape Town, someone in Durban and someone in Pretoria ever got together. And the reason was that Gaëtan was a PhD student of mine at the University of Natal, and the three of us worked together for some time on the problem I'm going to talk about. In some ways, it's a pity Gaëtan isn't giving this talk because he's put an immense amount of effort into his thesis, and all is over now, and he's busy at the MRC, and so I'm going to talk about the problem and how we tackled it, in some senses anyway. The setting is a relatively simple one. We have a binary response with a probability P of success. We have two explanatory variables, and we're going to pop the interaction in with them, and we're going to ask the question very simply, what about locally de-optimal designs? The model we chose, because there are a great many models out in the sort of pharmaceutical type of literature, is a very simple one. Just logit P is the usual sort of beta naught plus beta 1 x1, beta 2 x2, and beta 1 2 x1 x2. Much of the context of what we were looking at was essentially in terms of drugs, and therefore drug synergy, antagonistic drugs, and additive drugs. And for that reason, the interaction is of great interest. And just adding another little term, because it'll come back to haunt us a little bit later, also relative potency is very commonly defined simply as the ratio of beta 2 over beta 1. So somewhat to our surprise, there really seems to have been very little reported on this, only later on we realized why. In fact, it's, well, I'll be telling you why. First of all, there was a PhD thesis by Petro Kupchak. He was supervised by Nancy Reed at the University of Toronto, and he focused particularly on hypothesis testing and then design for the interaction term beta 1 2. There's a wonderful technical report by Gier and Myers that again was never published. That was at the at VPI, and they focused on, I want to go back for a minute, they focused on a very neat way of sort of exhibiting the designs that we're going to talk about, and so their particular approach we picked up. Finally, Tim O'Brien has a series of conference talks and papers and sort of articles. He was primarily concerned with what are termed ray designs, where you will put design points along the line where the concentration of drug 2 is proportional to the concentration of drug 1. So our first take was this, that there is a multiplicity of designs. The poor Gaëtan, the minute we change the parameters, the minute we change the constraints on x1 and x2, another design seemed to pop up. We had 4-point, 5-point, 6-point, 7-point, 8-point designs. It was a little bit of a nightmare. And in a sense, therefore, I think we ceased to be surprised that the problem hadn't sort of been tackled in a systematic way. And so two questions were really posed. The first was, can we somehow develop a taxonomy of designs? Can we sort of say, look, if beta 1 and beta 2 are greater than naught, and beta 1, 2 is greater than naught, then we get this sort of design, and so on. And the other question, having listened to Wenke, is just simply the beauty of the algebra. Can we prove anything? Certainly the taxonomy we could attack with numerical optimization. The algebra was a little more subtle. So that was the first take. And in the end, Guyton's thesis was primarily concerned, and this is just preliminaries, and you'll see why I'm doing it a little bit later. We looked first at the no interaction model, and his thesis in the end was sort of about 80% on this, and then 20% on the interaction model. So there is U is logit P, is quite simply the beta 0 plus beta 1 x1 plus beta 2 x2. And you have lines of constant logit, and this was the approach that Jerome Myers used, and it's the one that has suited us very well in what we did later. So there are the lines of constant logit, and from that we were striving to impose a sort of minimal number of constraints on x1 and x2, and so the first type of constraint was just imposing a constraint on x2 and just finish up with a design plus or minus u star plus or minus b. U star is the value of the logit instead of x1, and b of course is x2. Now Wenke posed a question which we also found very interesting, which is what is u star? We all know it in certain cases, but in fact you can think about k variables. Just expanding, this is a small digression just for a moment. You can think about having k explanatory variables, and then your design is plus or minus u star, plus or minus b1, plus or minus b2, and so on. Work that's been explored quite extensively by Ben and his students. And u star solves that equation. Again, one can show it, but what about proving it? And it has been done in a very interesting paper by Yang, Zhang and Huang that has just appeared in Statistica Sinica. They used some methods that were developed by John Stufkin and Yang based on arguing on the law of ordering of matrices rather than on the equivalence theorem. What we had in our little bag was actually a proof based on the equivalence theorem, and so we like to think that ours is perhaps slightly more direct and certainly gives some closure to the sorts of arguments that Ben and his students have been working on. Anyway, just to finish off, out of interest, the value for k is 2, is u star is 1.2229, and I've put k as 1 in because that again will come back to haunt us shortly. Let's just have a look at another type of design that we also focused on. We felt this was quite real because if you take x1 and x2 to be doses, then they're going to be greater than or equal to 0. And if beta 0 is minus, there's the magic number already, 1.5434, we get a 3-point design that looks like that. And if beta 0 is greater than the magic number, or minus it I should say, we get a 4-point design that rather neatly looks like that. We like to think, or Guyton, we have proved that these designs are locally d-optimal. I had a proof that I presented at MODA some 4 years ago for a rather specific case, and Guyton has now sort of extended all that. But I'm not really talking about the problem that I was initially going to talk about. So let's have a look at some of our results. And our approach runs a little bit like this. Here is our model, and the first question is, can we just simplify it down a bit in a canonical way? It's not entirely easy. The canonical tricks that were used, for example, by Ford, Tornsey and Wu to sort of simplify things sort of fade away a bit. You can't escape from the product term x1, x2. But you can transform, and I'll explain a little more of the geometry of this in a moment. If we do that magical transformation, we simply finish up with a very simple model like that. U is b0 star plus beta 1, 2, z1, z2, and beta 0 star has the expression that I've shown. Oh, I don't know how to make this shine. No. Did I do it?
Yeah.
Oh, there it is. Okay, there's beta 0 star. So, let me just show you First of all, a few notes. I'm going to show you shortly a diagram that will just reinforce what I was saying there. But before I go on, I just want to sort of make certain comments, because I talked at the beginning about the taxonomy. I'm actually zeroing in somewhat now. You can go on and on about what is beta 1, beta 2, beta naught star, and so on and so forth, and its relation to beta naught. I'm just going to show you a single case. We're still busy trying to get all the pieces of the jigsaw together, but these pieces were particularly attractive, and that's really what I'm talking about now. And again, just another small note. Once in a while, and I have actually done it already, once in a while I'll talk about x1, x2, sometimes I'll talk about z1, z2, sometimes I'll talk about the Logiton x2, and sometimes about the Logiton z2. And just another small note, and these are sort of technicalities to explain the pictures a little more. If x1 and x2 are 0, then they are lying on the logit line u is beta naught, and similarly there. But anyway, let me get on to the pictures, which, as I say, we have 4 parameters, and the beauty of these sorts of representations, oh dear, sorry, I rushed. The beauty of these representations is we have 4 parameters, and we're now looking at them quite simply in 2 dimensions. So, lines of constant logit, again, one's got these subtle little inequalities creeping in. The lines of constant logit look like that if u is greater than beta naught star, and lines of constant logit look rather like that if u is less than beta naught star. So let me move on, and let's just try and think about a design. Again, I'm searching for designs where we're imposing very few constraints on our x1 and x2. At the moment, I'm just going to live in the z2 world, and if you think about the pictures I've just shown you, the beauty of the z2 world, it's a very simple linear sort of movement of the origin. The beauty of the z2 world is you're just centering those hyperbolae that we saw just now. So let's have a look, and I've just imposed a constraint of z2 is plus or minus b, and there's some subtlety in that. The problem is, because we have the hyperbole, in a sense we're not cutting off our bounds of u star and minus u star. There are many designs that have z2 lying between plus and minus b, with u's that with z1s that carry on up here and down there, that are very much more d-optimal designs. In other words, we haven't constrained enough. Guyton and I were excited initially about this result, so let's just have a look at the details. And when we started to look more closely, we hadn't got z2 lying between plus and minus b, we had it fixed right there. And in fact, our design looked precisely like this, with u star the magic number, 1.5434. We produced a nice proof, and then we thought about it again, and we realized that in fact it was obvious. If I fix, say, one of the z2s, then I'm in the univariate logit context, and so k is 1, u star is 1.543. In other words, if I just very quickly, oh dear, I don't, oh, there it is, there it is. If I quickly zap back to that picture, we're just in a sort of very simple univariate situation, and we haven't really imposed a constraint. So, sorry, let me hasten on. We then had a look at what in a way seemed to be slightly more rigorous constraints. It's our doses again, real doses being greater than or equal to 0. And again, I've just made an odd little note. Let me just explain the picture a tiny bit. I've now got the coordinates z1 and z2 there. And so basically my hyperbola relates to the z-axis, but my constraint is a real one. It's not on Z1, and, well, it is on Z1 and Z2, but it relates to x1 and x2 being greater than or equal to 0. And so I've imposed the x2 is naught, x1 is naught lines. And this is the design that we got. And it is, in fact, when I say we got it numerically. I'll talk a little bit later just about what we think about proving all of this. It's actually an extremely attractive design because, let me turn on to the details of it. Here, first of all, is the condition under which you get those types of 4-point designs. Our magic number creeps in again. The design points look like this for x1 and x2 at the origin, 2 points on the same logit line as I showed in the picture, and then finally a very nice point on a ray, and the ray has the slope of 1 over relative potency. And if you recall at the very beginning of the talk, I said that was going to have a little bit of meaning once we got going. And so why? Well, intuitively it's immensely attractive. Guyton assures me that he has a proof. I'm a little more suspicious right now, which is a mean old supervisor, I guess. So at some stage we've really got to sit down and see whether we can just get out a nice result analytically for what we certainly have found. Well, as I say, in many senses he has got this result out. We haven't, using the equivalence theorem, proved the global optimality. Let me just carry on again, because if you recall, when I had no interaction, I simply had a 4-point design. And now if we have a look at the type of design we get, same sort of scenario again. I have the axes Z1 and Z2. These are my lines of constant logit and their neat hyperbola relating to Z1 and Z2. There is x1 is naught and x2 is naught. And again, we're almost sort of emulating the no interaction design. We have 4 points there, there, and there lying on the x-axis, and we have 2 points now on the ray. So this is a 6-point design, and let's just quickly glance at the details. The condition, I realize, is really quite simply once beta naught is actually greater than minus 1.5434, the magic number, then you get designs like this. The design points are on the same logit line, 2 more on the same logit line, and then 2 points on the ray with a slope of 1 over relative potency. And proof, as I say, analytically, if we sort of plug various things in, you can see that this is the best 6-point design under these circumstances. Proof of the actual optimality is something we're still trying to refine and sort out a bit. So let me just now, I've done this in record time, I see. Anyway, conclusions. Okay, looking at a binary response in 2 variables. We focused more particularly on the algebra and the patterns, and we're fretting a bit about the proofs, but we're confident with the patterns that we've shown here. Taxonomy for x1 and x2 greater than or equal naught, because that seemed to reap quite nice results. There's lots and lots of questions, and this is where ringing all the changes. I had, and I didn't emphasize it too hard, beta 1 and beta 2 greater than naught. What happens when they're the opposite sign? What happens when beta 1 is less than naught? Guyton has got all this sorted. It's a very neat taxonomy. Beta 1, 2 less than naught tends to be a sort of reflection of beta 1, 2 is greater than naught. And finally, the other thing that, in a sense, can only, I think, be done by numerical methods is starting to constrain x1 and x2 even further. Seeing I've got a few moments, I just could go back to one of my nice pictures and just show you, oh dear, it's going to take longer than I thought, just show you the sort of, oh, there's one, I think. Oh. Yes, What I basically mean by all of that is, what if we put an imposition on our x1s, not just x1 greater than or equal to 0, but say less than or equal to b, x2 similarly. Then you start to get rather odd designs. You're working at uncomfortable boundaries. You generate lots and lots of designs, and I don't think that nice equivalence theorem type of results can be gleaned from that sort of constrained situation. So I'll zap through again to the conclusions, and as I say, I'm happy to answer any questions. Thank you.
Questions then? We're lunch at time. Oh, I can ask two things. Randy Sitter and I had looked at two variables and then higher dimensions. And
Yes.
we standardized, but no interaction, but we standardized.
Yeah.
We'll let Z be beta 0 plus beta 1 x1, beta 2 x2, and another transformation, and worked out optimal designs with no constraints on the key linear function, the logit. But we needed the constraints we assumed on the other, and then you could, having worked out optimal designs for the whole interval, unrestrained values, you could work back to results for finite limits. One was on a mode of proceedings and one was a statistical.
Yes, we have the papers, Ben, and I'm trying to think now, because we tried to tie up our work with all the things that you've done in that sense. But the interaction term is a very nasty beast, and I'd be very pleased if anyone knew of other work that people might be doing on it.
One other question, what about taking the logs of the x's so that you remove the constraint of positivity? I've seen those response models that are logits and the log those rather than rhodos.
Yes, I mean, we could go back again to the first logit lines I drew out for the interaction model, and I said we had to fix B to get a design. Technically, you then have to also have a constraint on x1 and another constraint on x2, and then it's confined into a rectangle. Yeah. And then we got 8-point designs for that. It goes on and on, which is why I wanted to simply focus, give people a bit of a sense of how we've approached the problem.
Yeah, Andrew.
You had this picture. Can you? Well, you probably can't. If you can remember the number, yeah. Well, you had. It was supposed to be Z space, but the x's were straight lines. Is that right? Okay.
Yes, because I just transformed Z1 is x1 plus beta 2 over beta 1 2. It was just a linear transformation.
These are the same as I don't know, 4 tours neon rouge Z's, are they?
No.
Ah, okay.
No.
And
I think
then.
that was a point I touched on, that they have a lovely canonical representation.
This isn't.
And you can't do it here. In other words, they write
You can't do it with the interaction term.
because of the interaction term. So mine was a total.
Can you not do it for everything else and then see what the interaction term looks like? Does that
Well, that
mean
in
anything,
essence,
or?
I think, is what we finished up doing.
Okay.
I've lost it now, Anthony. Sorry, hang on. If we go back one, I think.
That's all right. I'm just trying to remember the pictures that I used to get on this stuff.
Yes, it's getting that interact. I mean, this is the simplest sort of way in which we could do it all. We tried this idea of, I think it's U. You can introduce the logit. U is beta 0 plus beta 1, x1 plus beta 2, x2.
Yes.
That was the canonical representation, and then everything sort of falls out beautifully. I was actually fiddling the other day. I don't see that you can trick this thing because you cannot escape from the interaction.
No, but I gave up at this point. The only other thing is, when I was doing the one without the interaction, I proudly got a 6-point design.
Oh yes, we
Yes,
do.
and then Tim Waterhouse said, "Oh look, that's just a convex combination of 2 3-point designs." So perhaps your 8-point design might be a convex combination of 2 4-point
because
designs.
I think, again, as I said, I restricted myself quite a lot.
Sorry, this is all a bit specialised. Those of you who haven't spent your time trying to.
Yes, trying to get these wretched things, but for us that have, it's very meaningful. Yeah, Anthony, it's this one, I think, where you put a constraint
Yes,
on.
that's quite right. Yes,
yeah, so you put a constraint along for
Yeah.
two x1s and a constraint for x2, and then if you squeeze it, you finish up getting points. Yeah,
Yeah, and you get points at the boundaries
at
as
the
well.
boundaries and
Yeah,
so on.
that's right.
And those are, I think, I just focused on this. Yeah.
Any more?
Can you just hand Wayne Key your information matrix so we can see his
The swarm.
No, he should do
check
this.
all your results?
He should do this NS series.
I'm going to run away and have a little swarm of bees converging, I think. It's very tempting. Anyway.
Okay, I think we should finish up now, and we can swarm around the posters.
Thank you.